everyone. Thank you for joining DataCon LA 2023. We're starting our next panel for right size, right time, cost-effective scale for game act backends using MongoDB with Sig and Kunal. Yes.
All right. Hello, everyone. So I'm Sig Narváez. I'm joined today by Kunal. So this is probably the only talk at the DataCon that is not about data science. This is really more an operational, data story, I guess, and how you can apply an operational backend like to games, right? So I'm joined today by Kunal, who is a real practitioner, right? Currently with Riot Games, formerly with that game company. And you have an amazing story. You've done amazing.
Hello everybody, thanks for being here, we appreciate it. My name is Kunal Lanjewar. I'm currently staff engineer at Riot Games. If you play Valorant, I work on Valorant. Prior to joining Riot, I was working on Sky Children for Light, who was made by the Journey creator, that game company. And I'm here today to share some tidbits from my time here and working with MongoDB. But if you haven't played Sky Children for Light, it's free to play. It's platforms. It's beautiful, non-modern game. An amazing social experience. I recommend trying it out.
Awesome. So this stuff was actually presented at GDC this year earlier on, but it's modified slightly, obviously, here from real world experience from Kunal. So let's get started. So first of all, we have made MongoDB. We've made a full stack demo that's available on GitHub, and I want to put this up there. If you guys want a screenshot or maybe scan the QR code. Most of what we'll talk about today is implemented in this demo. That's how we're going to GitHub. It has a Unity client calling out to MongoDB, has a backend, uses charts, uses an actual global cluster. So you can still use like a free Mongo cluster as well, and also charts. Okay, so everything is out there. All right. So this talk was inspired by, as we all know, right? Earlier this year, there was a lot of pressure in the tech industry about cost, and I think there still is. Although to some degree, AI, which we're hearing a lot right now, has sort of I guess changed that curve because companies are investing again, but in AI. But earlier in the year, there was a lot of pressure on cost optimization. And actually, Kunal, you have a story there about what you're doing at Riot, right?
Yeah, it's actually very true. So FinOps has become very real at Riot in the past 2 years. There's now a cloud excellence group, a center of excellence group that is monitoring expenses and putting pressure on teams to make sure that we pay attention on the systems we build and their cost.
Exactly, that's what FinOps is about. It's about developers being more accountable as to what technology you choose, how you use it, and obviously what cost it implies, right? And for gaming, where competition is extremely fierce, making sure that you are optimal in what you choose and how you use it is paramount, right? Let's talk about players. All of us here are players, and I've been playing since Atari 2600. I'm old. I have white hair in my beard, obviously. And so, MongoDB is used today in a lot of games to store, gaming profiles, to store matches, sessions, what you buy. Who's used Mongo, by the way, here in the audience? There you go. How do you compare that using JSON to the traditional database system? How do you guys like it? Or not like it? Love it? All right. So here you can see an example of a JSON document model, but I actually want to pass it over to Kunal, who's used this for real in real game.
So real scenario, while I was working with Sky. Sky took about 7 years to develop, and what happens when in game development, the services side comes later in the life cycle of the game development process. So at that time, Sky made a decision that, hey, we'll use Postgres because that's the expertise we have right now, and we'll start with a monolith application, right? It's an Erlang application. Most of the business logic then we started writing in Postgres. Whether or not that's a good decision, we'll find out. So what ended up happening is Sky then ended up launching on iOS, and the telemetry data that we were receiving, we could project that once we sort of launch on the rest of the platforms, which would be PlayStation, Android, or the following launch in China, the current infrastructure would not sustain this. And we need to find a way to sort of solve that problem. What ended up happening is I found the pattern that is called now. It's called Strangler pattern. I just found it 2 days ago that that's what it's called. But all it is basically you slowly migrate the systems that are giving you problems into the newer systems that will solve the problem. So what we ended up doing is we went back to the board and looked at Sky's schema design, and we thought, hey, you know what? These are the problem areas. So one of the biggest problem areas was checkpoint system. It's the game save system in Sky, which auto saves your progress in the game. You don't need to do anything as you play, roam around the world. The services sort of save your data as you go. And that doesn't need to be relational. It could simply be a JSON document of your transform in the game. And we just need to know your play ready, and we can just throw it in as a JSON document in some database. The problem with Postgres was that one, we had to do a lot of queries, and there was a lot of relationship involved, and all of the writes were going to a single instance. And obviously, as the data size would grow, we would need to somehow shard the Postgres, and that is a humongous task. And with a NoSQL database, we could solve that problem because of that. Like, for example, MongoDB auto shards the cluster for you and manages and does auto balance for you. So that will be a great benefit there. Storing your data as a JSON has another benefit, meaning you can actually do embedded querying of your data, meaning if you have a lot of arrays in your data structure, you can set up a embedded index on your array field, and you can only look up the specific element you want to look up. You don't need to query the whole document, right? And the other one is denormalization transaction. So we had a lot of normalization in our relational tables in Postgres. We didn't really need that, right? Like we could leave it, we could denormalize it, make it a JSON document and throw a key on there, and we would be okay with that. The downside is now you denormalize your data structure. Now someone has to aggregate all of that, right? Like you could solve that by aggregating on the application layer, and that's fine, right? We could live with that trade-off, and that exactly what worked for us. What it did give us is be able to horizontally shard your data across your cluster, and now you can horizontally scale and spike for my a few megabytes of data to, I believe it's like few terabytes, yeah, and we were able to sort of handle that pretty easy just by the document. So iOS also to Android, right? We launched into Android, and from iOS we basically the growth was exponential. We hope for about 1 million CCU meaning concurrently connected users at peak. It surpassed way more than
That's what we all want, right? Like if you guys are thinking of developing a game, you want the game to be massively successful, right? But you don't want your game to then be super slow because you are massively successful. So, okay, so now let's talk about what does it mean really to be at scale, right? So that document that we saw before, let's imagine that's a much bigger document, and maybe your player profile document is about 20 kilobytes, right? Let's just imagine that. What does it mean if you have 10 million, 100 million, 400 million, maybe a billion players like PUBG? Right? PUBG has actually by now it's probably 2 billion players. What does it actually mean? Well, it means 200 gigabytes, 2 terabytes, all the way to maybe like 20 terabytes. So that's a good size, but that's just data at rest, right? It's not it's not that exciting, and it's also not that expensive. The real challenge, of course, is with data at motion, right? Because remember, and put this in your head, right? At scale, every byte counts. Always keep that in mind. At scale, every byte counts, right? So now let's imagine that 60% of your players all the time, they play about 2.5 hours a day. Maybe your game, because of how it goes back to the backend to save data, to read it, and so on, maybe it makes about 75 calls per player per day. And your cloud provider, most likely AWS, charges you 8 cents to 12 cents per gigabyte of egress. Now think about all the traffic going in. What's it mean in terms of cost? So 6 million players, maybe 600 terabytes a day, about $100 a day, all the way down to if you have 600 million players, you could be spending well over $100,000 a day just in network egress, right? That's just only saving. What about as your game? Depending on some games are more write intensive or more read intensive, some games are more chatty than others. So this is just an estimate, but in real life, I'll show you a graph shortly of a game that was suffering from high network costs and help them optimize. Okay. So what could you do as a developer? Well, obviously, one easy way to do this is to control what you actually project over the network. Now, MongoDB, and most people don't know this or don't turn this on, not being aware, is that we compress data already from client to server naturally. It's already built in. All you need to do, as you see in this example, is simply add the compressor, the network compressor in your connection stream. Snappy, CLFC standard, and you can see the different compression ratios versus CPU trade-off, right? In general, right now, C standard actually gives you kind of best of both worlds, okay? And that's built in. You need to do anything other than just add the compression. Okay. Simple as that. Simple as that. Another thing you could do, of course, is control how much you project. And an easy way would be to project the fields you only need, right? You can create views as well. But if anybody has sort of GraphQL, right? GraphQL is an API layer construct, right? Pattern, where really now the clients determine what data they need to fetch. So in this model before, it's the database of the backend sending the data and specifying these are the endpoints that is still being projected. That's great, but you also don't want to change your code every single time, right? So with GraphQL, it's the clients now to specify. So maybe they want that projection there from the player profile, maybe other parts of the game or other standard arrays need more or less data. You can just express what fields you need to retrieve, and that will also be optimal. Okay, and that's built in, by the way, also with Mongo. So here's an actual picture of the billing chart for one of customers in the mobile space, mobile gaming space. You can see that the green part is how much network costs they're incurring every month. I can't show you the actual dollars, but yes, it's what's in the thousands. That range is in the thousands for sure. Actually, more than tens of thousands. So you can see after they implemented compression, they watch what they were projecting so much. You can see now how really they were. So again, remember, at scale, everybody. Okay? And of course, Atlas has a lot of all right. So let's talk about, let's go beyond just, theoretical data network and think about what a game backend actually looks like in terms of the microservices of the endpoints, right? Any game will have achievements, profiles, exactly, right? Sessions, matches, purchases. Think about everything you do with a game. Most of those will be a microservice or a domain of your backend. The reality is, as Kunal was saying, it's usually not just one database behind a service or everything. You probably will have multiple things. Like in this diagram, you see, there are relational databases, document databases, graph, key value stores, data warehouses, and all of a sudden, and this is true of any gaming studio, right? Or actually in the gaming company, you'll find yourselves doing ETLing of data between databases, sync, and much more. So it can actually get really complicated. A large-scale game can actually have a complicated. It's got to be a simpler way to do this. And so with MongoDB, one of the things that since we were founded more than 10 years ago, our founders felt that there should be a way to work with data, right? Have the database do more work than different databases, for example, kinds of databases. So imagine that all these microservices are now running on Mongo. What would that mean? Okay. So Mongo has already built in a cache. It's called the WireTiger cache. The WireTiger is a storage engine. It has built-in cache. It's an actual screenshot of the same mobile game that I was talking about earlier on, how every query is doing sub-millisecond reads because they're essentially, that data is properly cached. So player logs on and the profile is loaded, now it's cached, every read to them is going to be 0.3 milliseconds and 0.5%. That's what you need in terms of game. Super fast, sub-millisecond query response. And again, it's just Mongo, it's just Atlas built in databases. So now from a cost perspective, making a microservice is much simpler from that perspective versus all the others, right? I can really bring down your cost and your ability to launch. But speaking of game launch, let's imagine that you finish your game, you're launching, and maybe you run a post on the East Coast, right? Most likely in the US, you probably run East Coast since we have more area of the population. But over time, your game becomes wildly successful, and you need to actually account for global players. So there's two kinds of maybe workloads, read intensive and write intensive. For read intensive, what you can do with Mongo is simply have replica set spread out across multiple regions. Like in this case, my primary maybe it's in the East Coast right there, but now I have read replicas all over the world, right? And then you can implement a pattern called the CQRS pattern. I'm gonna pass it over to Dominic who actually implemented this for me.
So for, I guess CQRS pattern here would stand for command query responsibility segregation. And the use case for this pattern is required scale for reads, meaning your application needs to handle more reads than the writes. And this would be a great pattern to apply in your case, but there's a trade-off, like anything else, right? Distributed systems is mostly about trade-offs. There's usually no right or wrong answer, but it's all about trade-offs. You evaluate the trade-offs and find the solution not working out. So in this case, with that, you can see there's a user here. The way CQRS would work is you would basically, if you need to write your data to the database, you would route it through a specific service that would handle your writes, and it would go to a very specific database. And then once you need to extract that information, you would then query that same data or a transform of that data or a view of that model from a different database. MongoDB sort of does that for you with a read replica, so you can add read replica in your cluster. By default, it has a replica. Yeah. So if you route your reads to a replica set, by default it is pattern. However, there is a trade-off which I just mentioned. Trade-off here is eventual consistency in your data, meaning that the data you're writing, you may not be able to read it right away. So there's no strong consistency there, so just know that. CQRS also is an abstract pattern, so this is not the only application. For example, for Sky, one example I can come up with is, like I mentioned, the strangler fig tree pattern before, between when you were migrating from monolith to a microservice. There was this very specific piece in the monolith, which in our case was checkpoint system, that was getting, the inbox system, which was getting a lot of reads. And what that would do is, you would send your writes to the monolith, which is an older application, right? And then you have some sort of Kafka connector where it might be the MongoDB instance and a different service that is reading off of MongoDB, and then query that service separately. So that example here, I guess another example would be there's player support in the game. So player support a lot of times, if there's a downtime, what would happen for Sky is we would grant some amount of game currency as a compensation to our players. And it is a very low on writes feature and very high on reads features. So a player support person would go and say, you know what, for the Asia Pacific region, let me grant these players X amount of currency, and then when next day the players wake up, everybody's just refreshing their currency, right? So it's going to become an extremely high read service. This pattern would definitely help you separate your writes and reads, so your database that is managing the writes, which is very critical because you don't want to have any interruption there from the database that's doing all the reads. So the separation will help you. There's also a code here, some code here. This is from production code from Sky. So this is a global, this is written in Go, but this is a global database connection from MongoDB for that application. And what this is saying here is it wants to always prefer secondary database for reads, and there needs to be a majority on the data that is going to read from. Meaning that you can override this down the line, but CQRS suggests that you should not, you should follow this pattern, right? So you can force this on a global level in your application by writing, setting the configuration of the database connections.
I mean, it's kind of more about the recursive majority. So what's happened here is that you see the diagram where it says the primary database you will write to it, and you use the secondary, and it's called a node for Mongo. Secondaries. This is just a replica. And yes, it can be eventually consistent, but with that line number 10, right? Very concerned majority,
you can request that the document that you're going to read from the secondary node has been majority acknowledged. What does that mean? It means that it was written to one primary and also acknowledged by the majority of the other nodes, such that that essentially is the source of truth, right? If you don't say that, then yes, you could be getting an eventually consistent read. So the cool thing here is you can find it, right? So maybe other parts of the game you'll find with reading from a potentially eventually consistent, but some parts, maybe like your player name or your player currency, things like that, you want a majority, which is essentially strong consistent.
This one is really quick. So you can see secondary preferred, not secondary.
Yeah.
So this is something we realized in production. We were deploying a cluster which had a secondary instance at the time, and we instead of saying secondary preferred, we just said secondary. And we had an infrastructure bug where it ended up downsizing the cluster and we didn't have any secondaries at all. And what ended up happening, all of these started to fail. So what secondary preferred here says is that as long as you have a secondary, you would always go to a secondary. If you don't have a secondary, you would then only then go to a primary.
Exactly. Good learning there. So it's just a visual of the different settings, right? Primary, tag, secondary, nearest, and you can also say read from the nearest node. And our driver automatically keeps a latency, a ping latency of every node in your cluster. So it knows which node is the closest based on ping latency automatically. You can also do that as well. And like when you run with Atlas, you can, for example, create a cross-region cluster, like a multi-region cloud cluster. Every node will have metadata about what region, what tag it has, and so on. You can also use those tags to connect to those particular. That works great for games that are read intensive. But what about when it's write intensive? Right? If everyone needs to go and write to the same single region in the cloud, people in APAC are not going to be happy, right? Especially when you consider network latency across worldwide. Like this is AWS ping latency between all regions. So for write-intensive games, essentially what you can do is provide their locality. What you do in MongoDB is you shard the database. Okay, so you're going to shard your data, your cluster, you're going to put shards in different parts of the world. Each shard will have its own primary, which is write, and secondaries for capability for read, and there's different models here.
Still looks like
I could talk about sharding here. I think I initially mentioned that we were considering sharding to begin with. So the general rule is when in doubt, start with a sharded cluster, because later on, from moving from non-sharded, sharded could become an issue or not, depending on the database technology you're using. So if you have an option to start with a sharded cluster, start with the shortest sharded cluster.
two shards.
There you go. Okay. So for Sky specifically, as I said, we knew that we're gonna launch on other platforms other than iOS, like Android and PlayStation, and then China. Launching in China is always huge because there's a lot of passionate players in China. There's a lot of them. So your database grows exponentially. So we wanted to make sure that whichever database technology we use would support a seamless sharding.
Be able to grow, be able to add more and more and more.
Yeah, and I guess for the crowd here, what sharding would mean is that you have a huge amount of data set. You would then partition it in different databases so that it's not all in one place, right? So that would help you also when you have very intensive application, you distribute your writes to different nodes of the databases rather than all of them going to one spot, right? So that elevates all the bottlenecks you would have just have one shard.
And then just to explain quickly, there are three types of sharding. First one, which is here, is called hash. Essentially, we hash the ideal of the shard key. And that will give you a perfect random distribution across all nodes. Essentially, if you have 10 terabytes of data and you have 10 shards, pretty much each shard will have 1 terabyte. It will be perfectly distributed. So all your queries will go to one or the other, right? Then we have range. We essentially think about letters from A through C. You can say anything from A through M goes in shard 1. Anything from N to P goes in shard 2. So on and so on, right? So it's more like range. You kind of divide segments, And then zone is more about putting sort of a tag or a metadata name. I would say all these shards belong to this kind of zone. It's called North America, APAC, or maybe active players, inactive players. More like giving a name to a set of shards, right? Okay. So for the pattern we can apply for player profiles in particular, and for gaming, we actually combine two. We combine zone sharding with hash-based sharding. We're going to create zones based on like geographical areas, like in this case here, Americas and EMEA. Notice how Americas has 2 shards, EMEA has 1, right? And I can add more over time. And then on top of that, I'm gonna hash the player ID so that now all players in Americas will be perfectly distributed across Americas shards and then APAC shards and so on and so on. So all I know my players will be perfectly distributed in each zone. So now that kind of cluster is called a global cluster. Essentially, you could have 1 shard per zone or even multiple shards per zone. Notice here, North America West, LATAM, and EMEA have 1 shard, but North America East and APAC, the ones with green here, those you have 2. Maybe because they have just more player base there, right? That's fine. They can just have more capacity per zone. And so now that we think about their locality, what do the actual queries look like? We're in time. So this is a screenshot of a visualization of the queries being routed to 1 shard or multiple shards, depending on what you're querying for. I'm actually going to show this for real. We'll be a camera, I guess. Oh, cool. All right. So here is a real global cluster. Okay. So notice how that it has 3 shards, 0, 1, 2, different data sizes. Now there's more things running here, so but if we look at here, you can see that shard 0 is actually named Americas, running on AWS US East 1. Shard 1 is named EMEA, running on Frankfurt, Europe Central 1, so on. Now, actually, this one is even more special because what we've done, we've located each node in a different region. You can see here how every node in each shard is in a different cloud region. For example, the Americas primary is in Virginia, but then we have a copy in London and one in Singapore. And the EMEA one, the primary is in Frankfurt, but then we have Virginia, Singapore. So basically, we have a primary, and then its 2 replicas are in the other 2 regions, or the other 2 zones, I'm sorry. Okay. And finally, the primary is in Singapore, with the copies in Virginia and Frankfurt. Right? So, what does it actually look like? Let me switch over to Compass. So Compass is our kind of our workbench, right? Where you can text and run queries and see how they perform. So my data looks like this. Here's an actual player profile, very small. By the way, this is the player that won #1 when we had this demo at GDC this year in San Francisco. His name was Wolfels. He kept coming back and he won. So you can see here, I'm going to query for where the nickname is Wolfels, the location is US California. Right? If I do an explain plan on that, you can see that indeed it is hitting only 1 shard, right? The Americas shard very quickly. 50 milliseconds probably because of the latency. Because of cache. There you go. Now it's 1 millisecond. Why? Because that player profile has now been cached. Remember what I told you about? Now I'm doing a single millisecond. Let's do something more. What about if we go and say, I want to find out all the players we have, group them by location. I'm going to group by location, and then just sum of 1, and then sort them, right? Run. Explain. And then we see that query actually hit all 3 shards, 3 parts of the world, right? It hit every single shard, hitting the indexes and so on. It came back also in about a minute. It actually went up to APAC and EMEA and US East 1.
Did that actually do a scatter?
No, it's doing a. Actually, you are right. It's doing a collection scan. Yeah, it is doing a collection scan.
We have 1 millisecond.
Yeah. So you see in the bottom here, call scan just means it's gonna go through every single record, every single document. Yeah. We don't have a lot of data. 300, 301, 8, but still. Okay, so you can see how. So even though your data is distributed, yes, you can query out, and our engine will route the queries properly, right? Here's one for, now let's look at the recordings. So the recordings are when you actually play, right? When you actually play this game that we mentioned at the beginning. Is that too small? You know, we write down all your bullets, your points, whatever you did, etc. We write down who was the player. We write down every single move in the game. So you see the X and Y and Z. So every single path that the player took, that's the play. It's all written down in a single document. It's an array. Right? So here we're going to run now an aggregation that says, find me this player, this nickname, and so on. Right? Find, explain. So these are all the game runs for that player in that event. So again, 2 millisecond query. Right? Third one is, now let's actually do another aggregation. I'm going to find out, give me the global stats. So give me all the gameplays, give me the total damage done, I mean, sum of, and give me the average score. To go again against all the cluster, right? There you go. There's been 930 gameplays, that much damage. There you go. Now, how if this had a billion players, billion matches, and so on, sure, it may not be 7 milliseconds, but it will still be quite performant. Okay. Cool.
Beats having to maintain all those Redis clusters.
Yeah, how does it compare to running Redis and Postgres and everything else?
Depends how far Redis is. For example, for Riot, it's about anywhere from 5 milliseconds to 16 milliseconds, depending on how far Redis is.
Cool. All right. So, bottom line, MongoDB is used by a lot of games today. The world's largest game, I can't name it right now, it's being reported, but the world's largest video game, for you know it, runs on Mongo. So we do have a lot of functionality in the platform, not just a database. We have API layer, we have a Unity SDK, we're working on an Unreal SDK, and much more. It should have most of what you need to build a game. Right? So with that, I actually want to, if anybody wants to also scan this, we've done a series of podcasts for gaming, gaming customers, gaming use cases. You can see there Kunal right here. So we actually met Kunal at GDC 2022 last year. And I was sitting in this session. He was talking about Mongo rules. I'm like, who is this guy? He's like, we don't know. And after that, we met him. We had a podcast and so on. So check that out. It's a playlist of all of our podcast episodes. So with that, let's go over to Q&A. And I'll leave this up as video Q&A. So if you want to scan that and cloud and try it out.
Real quick, if you want to see how the full backend architecture for Sky looks like, it's on GDC Gold. If you just search Sky's journey to 1 million CC, that talk is on there, and there's also a lot of slides that will show you the architecture design there.
Can you pop up the other QR code for the
Minutes?
I'm not familiar about the data management and gaming industry, but I'm curious, what's the percentage of the data you just save in memory versus a database? Because I assume you don't have to save everything.
I guess it depends. I would say, well, probably save in memories.
It depends on the type of the game. So, for example, Valorant heavily caches because Valorant is not an MMO, and there isn't a lot of real time things happening there. Once you're in a game of Valorant, that's it. There isn't a lot to save. So it really depends on the game. There isn't really a set percent. but we do cache a lot. It depends also on what you're trying to cache for. Like you also have to ask if caching, is that something you really need? A lot of systems in Sky didn't even use caching. We just used MongoDB's the database cache itself, and that suffices for
Something you will cache at the actual game time. You avoid both network.
Can you give some examples about features that are heavy on reads, and some examples that are features that are heavy on writes?
for games specifically, or just in general?
For games.
Okay, so I mentioned checkpoint system early on in the game. Sky has a way to save your data as you are navigating around the world, and you as a player don't even know that's happening. And that so that when you get out of the game and come back, we make sure to have last 5 or 10 checkpoints that you've been through, because that also determines which quests we can unlock for you, what progression you're on, things like that. And that is happening every couple of seconds, so it's very heavy on writes. The other system I can tell you on writes is Sky also has a record your own gameplay option, so you can record your world, what you did in the game, for other players to see. So when you're actually recording, it's also writing a lot of data back to the servers, but that's also a very high read system at the same time, because other players are then going to see your recording that's put in the game to visualize how you actually move around. So that would be a system that does heavy writes and heavy reads at the same time. And for just heavy reads, Sky has an inbox system, for example, where you can send messages to your friends or basically anyone you're playing with in the game. So you just have to send one message. It's not a chat system. It's sort of like an email system within the game. You can send a persistent text to your friends. You can send that to, let's say, 50 people in your friend list, for example. That would be spam. But that would be a very heavy read system. You only write it once. All these 50 people are going to that.
A game that I used to play a lot that I know runs all the metadata about the characters, the items available, and etc. All that is like heavy read only, right? That was stored in a different chunk on the system chunk, right? Actually run at even higher scale, more memory CPU, but all that would pretty much be running for memory. Versus, sure, when a player plays and saves a match, that's very interesting, right? Some games right at the end of a match or something. Some games are actually streaming rights.
For Valorant, for example, if you open the store in Valorant, that's a very high read system, basically, because you're only publishing the store catalog once.
Exactly.
But then all these millions of people that are going to be online, very, very heavy on reads.
And that pattern with MongoDB, all you do is place reference. Where you good question, Federation.
Yeah, you had it. Okay, I hope you can hear this. So you flashed up something about analytics on your slide. Can you talk a little bit about how you do those and what kinds of analytics and how are they implemented, including things outside of MongoDB?
Sure. So, for example, with MongoDB, you can still do efficiency if you want to.
Second node, for example, also run those nodes supposed to be high tier. We have simple interface. It's a lot of tools like Tableau. We see a lot of research in types of queries, or rather, there's types of insight. Inside the the operational data, which would likely be in Mongo, and broader insight that we get from
other data, like your, let's say your iOS
purchases, much more. We need to combine that data together.
right, with the operational data, which is in Mongo. That pattern we usually see that Snowflake, where you can bring both operational data.
What we end up doing is we basically, there's an option to do analytical replica set,
And it will
and
bounce
then
it
a
up.
replica on your shard, which would be dedicated for analytics, and its performance would not affect production.
You're right.
And that is what we use for Sky. And we would basically send every cluster would have a single analytical reader instance, where I believe there's the connect, like analytics connectors will connect, we'll send it off to me.
And so are you doing everything in Mongo, or do you actually export out to BigQuery or Snowflake or some similar system?
No, we're exporting, at least for Sky, we're exporting out to other data warehouses.
Thank you.
So there's two types. We call it app-driven analytics, which is usually directly against the operational cluster. And then there's the more like the enterprise analytics. That would be your big critique.
Right, just figuring out like policies for handing out swag, stuff like that. Exactly. Yeah. Thank you.
Are we done? 20 more minutes. There you go.
So I'm curious, just kind of from a what you see in deployment perspective. I noticed that your demo cluster that you had there was multi-regional.
Yes.
And given that you kind of got a mixture of these read-intensive workloads and write-intensive workloads, do you see a lot of use cases within gaming where you have a write-intensive workload that needs to be deployed multi-regionally? Because I would imagine that like inter-regional data transfer really starts to bite you in the butt in the same kind of way that egress would pass to through.
Right. And so I guess the question is, for read intensive workloads, how can you avoid the network?
Really for write intensive workloads, because I would imagine you would have to have some kind of synchronization between your kind of the place where the write goes to initially and all the replicas of that write.
So I think it's going to be a trade-off. So let's imagine this one. So every box here represents a shard. A shard is 3 nodes, right? 1 primary, 2 secondaries. But the data is sharded. So a player that lives in the west will not be read from east or somewhere else, right? Sure. So the point is to basically provide a shard. You have their locality. So your writes and your reads are going there.
Right.
And everything your API layer will be also deployed in the same region.
So now you're just doing local.
I think also you're doing intra-region traffic, right? Which is
Okay. So you could imagine then, forgive me for the follow-up, but like you could imagine then that in each of your shards, your primary and your secondaries would both be located in the same cloud region, as opposed to having inter-regional.
shards.
So I guess you're kind of running the risk potentially of the region goes down, your shard goes down, but you're kind of expecting that that's going to be a pretty.
So you could still then have replicas from each shard in the other regions. You actually saw it in the live cluster I showed you. You actually have it set up that way.
Right. So then in that case, though, you do have to worry about data replication between those regions, right? Have you seen a lot of customers that have been bit by costs because of that?
It depends on, so how we get trained up on how right intensive are they?
First of all, that traffic is compressed by default.
Sure.
It's going to depend really on the customer.
Gotcha.
Well, we saw customers that had
A really large player profile, and they were fetching and every single time all the way. But that could cause the change a lot. So you write it, you replicate it once,
the other side, sure, but then it doesn't. So it's really depends.
Gotcha.
But it's a matter of understanding your work.
But your writes would not travel into region, right? Your writes would always, let's say you're in US West 1, you're writing US West 2. Is that your?
No, but we're talking about if you have replicas in other shards, in other regions of the same shard. So like if I had replicas of West here, then yes, every write will replicate, sure. But that's also it's almost like insurance.
Sure.
How much you want to pay for insurance, right? That's right. How much you want to pay versus how much you want to get covered. Right.
Usually you would have replicas across availability zones within the same region.
Okay, that's
It doesn't make a lot of sense from where I stand that you have replicas in an entirely different region unless you're doing something with like backups or fault tolerance or something. That is really the cost.
Yeah, and remember, it's a trade-off. Like if it's a game, no one's gonna die if the game goes up. Right. Money, sure. But you don't need with customer data or financial data, so it's
Thanks.
okay. Good. Last one?
Yeah.
Good. Okay,
All right.
all right, well, thank you so much. Again, check out the repo. Now, thank you so much again.
Thank you.
It's a pleasure. Thanks, everybody.